Welcome back to physical chemistry. Going on more about, oh hang on, let's have some light. Welcome back to physical chemistry. Let's have more things about light and think about a bit about the difference between heat and light here. I'm trying to work out what you're looking at. So what I'm interested in is if we have a set of energy levels like this, how do we determine which ones are populated? I've put them weirdly evenly spaced, but they shouldn't be, because as we know, if we have a typical energy well like this, which would be the typical one for a bond vibrating, and also very similar to the one for an electron going around an atom, because obviously it's not going to be the same, the electron trying to crash into the atom, as it is escaping. So we have similar principles involved, but if we have these, we would expect them to get closer and closer together as this side opens out, and so we would expect our energy levels to get closer and closer together. This isn't a physical example. What can we say so far? So far we can say we've got some selection rules. The selection rules for infrared and Raman, which are to do with the difference between the starting and finishing state, so there are rules about that come from quantum mechanics, but there are also some others that we need to know about as well. So if we think about this one, we can excite this electron or atom or molecule from this energy level, because we don't know what it is, to a higher one. But if we have a population of them, then it becomes more interesting. So let's have a population of these molecules or particles, whatever they are. They're all in the ground state apart from this one that's in the first excited state. We can first of all define that we would expect them to be in a Boltzmann distribution of states, and what that tells us is that most of them will be in the ground state, and if we heat it up we can promote them to higher excited states, but what we can't do at any point is have more in an excited state than are in the next state down. That is by heating it up. This is an important principle because it tells us something very useful. That means that if we heat it up, we're always going to have some down here. So if we're trying to do our spectroscopy, we can always do this transition between the ground state and the first excited state, even if we're at very high temperature. Because as it goes on, we go up and up and up. Eventually we get one in each, and then obviously statistics starts to go wrong because there's only one in each, so there could be none in the ground state. But if we have a large population and it's not very, very, very hot, then we will get some in the bottom, and so we will always be able to measure this transition even if we're much past the temperature where we can have enough energy to excite these other excited states. But when we have a photon coming in, we're allowed to excite them. So we can excite to any excited state, and we can generate particles up here. But now we have our laser problem. The laser problem is if we shine a light of this wavelength in, so the wavelength required to excite this state into this one, could be an infrared state, could be an electronic state, then the same light will also stimulate emission of radiation back down. And unfortunately for us, the probability of it doing that is pretty much equal to the probability of it absorbing one. So that ends up telling us that by shining light on, we can't make an excited state have a higher amount of whatever it is in there, higher amount of molecules, a greater population than the ground state, just by shining one light beam on it. So if we heat it up, we just sort of pile them up steeper and steeper, and if we shine light on it, then we're only using these two outside ones. The ones in the middle aren't doing anything, but of course they can fall down through them by thermal decay, because the system isn't hot enough to excite them up there thermally, but obviously if we excite them there by light, they can fall down through the levels in between. That seems reasonable. So the problem that we now have is if we want to make a laser, this will work against us. On the charging it up stage, we can shine our light in, and we can only excite half of our molecules maximum up to here, and it gets worse and worse and worse, because as we get closer and closer to it, more of the light that we're shining in is actually doing the opposite of what we want. When we get up to 50%, no matter how bright this light is, it's going to be knocking them down as much as it's knocking them up, and so we can't get any further. The problem then is this light isn't causing any, it's causing lasing, so when it hits one that's excited, it lasers, it gives out two photons, the one that went in and another one, but when it hits another one that's in the ground state, it promotes that and it's gone, so we get exactly the same amount of light out as we put in. That's not what we want if we want to generate a laser. So we have a little bit of a problem. We are going to have to do a trick in order to get our populations such that there are more in the excited state than there are in the ground state, some way of beating it. This brings us back to our difference between fluorescence and phosphorescence question. So if we excite a molecule electronically and it drops back down again, then we can get light back out. That comes out fairly quickly over a relatively short time scale. If we excite it and flip the electron over, because light doesn't contain a unit of spin, not only is it not allowed quantum mechanically to do that, it's also not allowed to drop back down again. And so if we do it accidentally or deliberately, then we'll end up with phosphorescence, which is a long-lived excited state that's trapped there because it can only get out by flipping the spin. However, it's very inefficient to get there. We can improve the chances of getting there by having heavy atoms on our molecule, and that will do something called spin-orbit coupling. So the spin of the electron that's required to flip the spin of the electron over, the spin momentum, rotational angular momentum required to flip the electron spin over, comes from the angular momentum of the orbitals. The small orbitals, the 1s orbitals for example, or any s orbital to be honest, they don't have any spin. The higher orbitals do. So the d and f particularly have spin units, and they can, if they can interact with the electrons to help them to turn over. That improves the chances. It's still quantum mechanically disallowed because it doesn't come from somewhere. We're interacting different things, so it's extremely unlikely. But because we are getting light out of a different color than we put in, we have the same advantage as fluorescence, that it's easy to detect even though there isn't a lot of it, even though it's not very efficient. Likewise, in our, I've put mine down in my numbers that you charge up. Oh no, here it is. In my dye that I can charge up and then turn the light off and it glows. I wonder if it will work. No, it's not going to work for me today. Needs more light. It's not as bright in here as it appears to be to you. It's actually quite dark today. In proper light this glows afterwards, but you have to reduce the light intensity quite a lot. To me it does look quite bright and green, but to you it doesn't. Where am I? So that's one possibility, and that allows us to do something that is difficult, so we can park some molecules in a forbidden state and they can't get out very easily. That's a way to do this problem. So if you are familiar with this, you probably are familiar with this, the simplest type of laser works with 3 energy levels. So if we take our bottom energy level and we excite to the top one using 1 frequency of light, it means that we can get molecules out of the bottom state. We can only get half of them up into the top state, so let's have 4. So we can put 2 up into here, and then they drop into an intermediate state here. We can park them in there, and as long as we can keep exciting the ones from the bottom into the top, they're all disappearing into this intermediate state, and the more stable it is, the better. So the more stable this energy state is, the more atoms, molecules, whatever energy states we can get in this intermediate level, and the lasing will happen between these two. This is typical for flashlight type lasers. They often have a fourth energy state and it's somewhat more efficient, but this is the simplest diagram that we can make. That means that this light here is obviously inefficiently exciting them and pushing them back down again, but all of the time they're dropping into this intermediate step in between. That's all very well and good, but why does it mix with our subject so well? Well, we've got another thing that can happen. In a carbon dioxide laser, we deliberately excite, or we deliberately use some of those states that are not infrared active. The selection rule for infrared was the dipole moment of the molecule has to change for a transition to be infrared active, for it to be able to absorb infrared light efficiently. Doesn't mean it doesn't happen, and that will make one of these useful steps in between if it's very difficult for it to do it, or if we can excite it a different way through another thing. A carbon dioxide laser uses carbon dioxide, obviously, CO2, and the interesting vibrational state that we're going to use is an asymmetric stretch where the carbon effectively moves up and down and the two oxygens don't move at all. So they're staying where they are and the carbon is moving from side to side in between. That doesn't have a change in dipole moment. It doesn't have a dipole moment at the beginning and it doesn't have one at the end. So it's not very infrared active. It's quantum mechanically not allowed, which means it's very, very weak. But we can excite it by hitting the molecule with the right amount of energy, and typically inside a carbon dioxide laser is another gas, usually nitrogen, that is excited usually electrically, and so we've got N2 which comes along and punches physically the carbon dioxide, exciting it up to a disallowed, quantum mechanically disallowed vibrational state, which means that it's stuck there. It has more difficulty getting back out of that state, so we can hang it there for longer. It's a useful effect of these not allowed quantum mechanical transitions, because now the carbon dioxide has energy, but it can't lose it very easily. Obviously, if we put too much nitrogen in there, then it can give it back to the nitrogen, but we have chosen nitrogen so that it has an energy level slightly above the energy of this asymmetric oscillation, and it doesn't have an energy level below it, so it can't easily give it back either. And then we're stuck, our poor carbon dioxide is stuck with this energy. It's a vibrational state, so it doesn't make sense to draw an electron there. It's stuck with this unit of vibrational energy, and it can only give it out by hitting something else, hitting another carbon dioxide, or emitting it. But because it's a different energy to what's coming off the nitrogen, it doesn't lase until we want it to, or until one of them spontaneously drops down, and then it fires the rest of them by hitting all the other molecules. And because there aren't very many in the next stage, because it's also disallowed, because it's also an excited state, that's better said, so our ground state's down here, because there aren't very many molecules in the next excited state, the chances of hitting another one and exciting it is lower. In our 3 energy laser that I had before, obviously a major drawback with it is that if we fill up this intermediate step, we still are always going to have some molecules or atoms, whatever they are, in the ground state. So when these drop down, we can also hit another one of these and knock it back up again, which loses our photon. It's wasting energy. If we've got a 4 stage 1, we could have an empty energy level here, so we get a very sharp peak of pulsed power. Obviously, as we fill this up, our energy in our beam is going to go down very quickly to half the level, maybe even lower. So to bring it to something that we already know about, if we have these normal, let's call them we'll call them the normal We work out what's going on here. Singlet state, because there's only one. So this is our S0. We have our vibrational states inside, and our atoms to start with, our molecules, sorry, because they've got vibrational states, they've got to be molecules, are all in the ground state. If we warm this up, we will get a distribution into the different excited states. It's very unlikely that we'll be able to do an electronic transition thermally, because by that time we'll have damaged the molecule itself by shaking it. But we can do an electronic transition with light. So in comes our light, and normally, as we were measuring before, we can have an infrared transition, which would be this one, typically like that. So that would be IR, and because we have excited states, we can also do this transition and this one up here. So we generate excited state transitions too. Let me rub those off, just leave one on, because otherwise this drawing is going to get very messy. The alternative thing that we can do is we can excite to usually an excited state, so we can do a normal excitation into an electronic excited state, this one here, and then it will do what we expect. It will decay down to the ground state, and then it will decay from there down to an excited state. If we measure the fluorescence, we can see that that's typically not going to be dependent upon the starting condition, on the temperature, but the excitation is, because the amount of this second excitation from a already excited state will obviously be dependent upon the temperature, because it depends on how many of our molecules have reached this excited state. Again, I'm going to have to rub it all out. This is going to be difficult. I might have to start again. So 1, 2, 3, 4. Okay, so that would be our fluorescence. If we want to measure a Raman spectrum, then we would excite from here. Wait a moment. I wanted to tell you something important about fluorescence while we were there. So in fluorescence, we might not be able to measure the temperature very easily, or we might not be able to see very many effects of temperature, but look at this. If we excite from here to this excited state, and then we allow it to decay back to the ground state, then we get more energy out than we put in. Admittedly, the overlap, which we had in our fluorescence part of this course, the overlap between this state and this state and the ground state particularly, is not great, so it's not going to be a very strong transition, but it is possible for light to come in and fluorescence to come out that is of higher energy than it was before. This is the basis of laser cooling, because if we can shine a light in at this frequency, we can excite the molecule up to the top, and it will go back typically to a lower state than it was before. It's not entirely the basis of laser cooling, but it's related. And now we get on to Raman. So if we excite something in Raman from here to a virtual state, let's put it in the gap here. If we excite it to a virtual state, it's obviously not going to be very likely, and it must drop immediately back out of that state, typically down to the ground state. It will be scattering. But the one that we want to measure is this one here. This would be our Raman signal. And as in the Raman lecture, we would plot the Raman shift, which is the difference between these two, against intensity. So we would get shift shift in wavelength and intensity, and we will get some kind of peaks. And those peaks are very similar to the infrared peaks because the actual transition that we're measuring is the same. What's interesting about Raman is, however, if we're already in the excited state, we could do exactly the opposite transition. So we could go from here, the first excited state, up to here, and then back down to the ground state. Which means that there is another Raman spectrum on the other side of the axis, and the higher energy than we put in axis side of the axis. So this is more energy, this is less energy, and because it's the same transition, we would expect to see the same peaks identically with the same distance from the origin, which is the laser color, as the actual peaks that we normally see. This is called Stokes Raman and this is anti-Stokes Raman, and obviously they're not the same size because they depend on the population of these two states. Very usefully, that could allow us to measure the temperature of this molecule in a solution from a distance, because the relative height of these two peaks tells us exactly how much of it is in the two energy states, and if we know what the difference is, which is effectively this distance, we can work out what the temperature is. It's very handy. So this will tell us the temperature of things just optically from a distance without any other sample probing molecule, without a thermometer, nothing at all. It also tells us something about absorption. So if we take a light source and we cause this absorption, we can tell from exactly from the laser effect that if we shine the light brighter and brighter and brighter, we will increase the amount of our molecules that are in the excited state. But when we reach a certain concentration, around about 50%, then it will not absorb very strongly anymore. In fact, if we get to exactly 50%, it won't absorb at all. It will scatter it, so it won't be as bright as it was before. But if we're using this as goggles to protect us from some bright light, it is an issue, because if we have too much, if we beat the threshold of our dye, whatever it is in our goggles, then it will be completely ineffective. It will suddenly go from being absorbing 99.9% of all the light to absorbing a small proportion, because the direction it goes is mostly forwards. In fact, it isn't a whole lot better than having nothing at all. So our laser goggles, if they use an absorber, have a problem that they will suddenly stop working if we make our laser too intense. So a low-grade laser goggle doesn't work with more powerful lasers. That's related to exactly this problem that we have, that if we excite with light, we can't populate it past 50%. We can skip over the levels in between. If we excite with heat, we can't skip over the ones in between, and so we have to fill all of those up like a little hill. If we suddenly fill up all of these thermally, then they got to fall down some way, and they can go down either thermally again, which means they will cascade down, or they can give out light, which means they jump down. And then the rules for what they do are different. It depends on the overlap between the two states, and whether it's allowed to do it, and how many are in each state. Whether it gets hit by a photon of the light that it's going to give out, which will stimulate it to emit, it will also push some more up. Okay, so that's a good cluster of themes for today. We can stop there.